continue from yesterday. This is about remote sensing and the technique about how we do the remote sensing. And I think a lot of students and participants today. And since yesterday, I got a lot of questions about the material. So we hope today we can continue this discussion and then continue the material. I will not hold any longer, and I think Professor Adam, maybe this is your chance to present the material. Professor Adam, the floor is yours.
Thank you, Jedfan. And once again, thank you for everyone for the invitation and this opportunity. I now recognize it's even earlier than I thought where you are, so 7 a.m. So thank you for that. And of course, if I show some slides that are hard to read at 7 a.m., just stop me at any point or mention it in the chat. So what I'm going to do is share my screen again. I did yesterday. So, yesterday we really talked about how remote sensing and geospatial information can be used in hydrology with some specifics to groundwater. Today, I really want to go a little bit more in depth about remote sensing in hydrogeology or remote sensing in groundwater. So that's what I'm going to cover. Just really quickly, if you're new to, you missed yesterday, I received my bachelor's at University of Buffalo. I worked at a national laboratory in the United States doing some remote sensing of aquatic systems. And then I received my PhD and postdoc in hydrogeology remote sensing. And I've been now a professor here at the University of Georgia. I often use a combination of interrelated data sets and techniques to try to understand these complex problems. So remote sensing GIS is going to be an integral part for a number of reasons. And you'll see again some of that today if you haven't seen this yesterday. The last part that I mentioned yesterday was that we still always have a need for remote sensing. This isn't just as an augmented tool, but rather it might be the only tool, in 10, 20, 30 years from now, because our global networks of trying to monitor elements of the hydrologic cycle are becoming decreasing over time. This is discharge. So they're spatially not really represented, and they're also temporally becoming less and less. And so the need for remote sensing and the data scientists like yourselves is going to be ever increasing over the next 10 to 20 years. So I mentioned this yesterday, and I'm mentioning it again today. Remote sensing field as a whole has grown a lot over the last 20 years. Yes, satellite-based remote sensing started as early as the 1970s, but we had very few sensors and very few capabilities. It wasn't until around the early 2000s that we really started to take off, because we had the technology, we had the economic ability to put more satellites. And today where we are is that every single element or process or reservoir within the hydrologic cycle is capable of being estimated via space. Okay, so it's a key term. We're not measuring it because we're not actually measuring any of these variables. We're estimating them, but all of them can be estimated via space. Some, of course, are going to be more accurate than others. For example, if I'm looking at stream flow or surface water down here in the bottom using something called NVSAT, SWAT, or Topex Poseidon, if we're looking at lake levels, that is considered fairly accurate at this point. We can have a high degree of certainty that the lake level via space is going to be the correct value. We get into precipitation, things like TRMM, SSMI, now the most recent called Global Precipitation Measurement Mission, GPM. It can be very accurate depending on where you are looking and where is your study area. But then you move into some that are still in the infant stages. Now, I'm going to talk a lot about this today, but we're thinking about water storage. Water storage is from GRACE, a satellite called GRACE, ASTER a little bit, and then something called the GRACE follow-on mission that was just recently launched a few years ago. This would be the one where we're still learning, we're still developed. Most of the science is trying to understand groundwater dynamics, not just because it's important to think about groundwater sustainability and how we might be able to engineer solutions, but also because this is the one that's most difficult to measure from space or estimate from space because we're really trying to now get into the subsurface. And so this is going to be one I'm going to spend a little bit more time on today. So when I'm thinking about groundwater and remote sensing, it really comes down to two main factors. Okay, so what we can do, what we're capable of in terms of satellite-based groundwater measurements. The first one is groundwater potential mapping. So what that is a series of statistical or probabilistic models. I wrote the most common one. We call that a frequency ratio modeling. I can get into that in the Q&A if you would like. But ultimately, what we're doing, you could do this without remote sensing, right? These are just statistical or probabilistic models that state, if I think about X number of variables, call it 10 to 15 variables that would contribute to groundwater variability or recharge or the potential for infiltration. What I'm trying to do is really take these 10 to 15 data sets, integrate them spatially and temporally to be able to predict where I have groundwater potential. That's the main field of groundwater potential mapping. Of course, just like I showed you the monitoring networks being depleted, it's the same thing is happening here, right? So we don't have enough data for these 10 or 15 data sets. We might not have topography, geology, infiltration rates, slopes, land use. We might not have that on a scale, a large enough scale based on field data. And so really the push over these last 15 years is to utilize and replace the field data or augment with remote sensing. So for example, we're going to get topography from an astro satellite. We're going to get aerial photographs from UAVs or airplanes. We're going to get land use and geology from ASTER and MODIS and Landsat. And that's a big part that's been happening. In fact, I can show you on the right, I stopped this from a 2012. So pardon me for not updating this. But of course, you can imagine it's going even higher. These were the number of publications that included groundwater and remote sensing in its name. So all the publications worldwide that were published in these certain years. And you can see in the 1990s, we only averaged about 20 publications per year with groundwater and remote sensing. Now into the 2000s, starting to increase. 2012, we're about 140. And now I do know we're about 300 to 400 papers a year on groundwater and remote sensing. Okay, so just imagine the trajectory we are on based on the science and the capabilities. The second thing, and probably where you see the most applications of groundwater and remote sensing, is when we're trying to think about groundwater storage and or processes. And I'm going to go over the third one primarily today. I'll just briefly mention these two. And again, I welcome them in the Q&A. But the first way, the older way, in the early 2000s, there was a seminal paper in 2006 by Matthew Becker. It was a groundwater review of groundwater and remote sensing. It really is the first paper that addressed groundwater and remote sensing. And they looked at using ASTER, which is a thermal emission radiometer. So if you think about that spectrum we spoke about yesterday, this is where we're looking at the thermal wavelengths. And all we're actually measuring is the heat capacity of the material. So we know that there's diurnal temperature changes. And so what would happen, of course, is if I look at day and night images, I can actually see if the soil is wet or moist. Okay, this doesn't say that I have groundwater. This is a key distinction. This just tells me where I might have had an infiltration event, where I might have saturated conditions, potentially tells me where springs might be located. So this isn't going to really identify how much water is anywhere at all. Maybe not even necessarily a process, but it's going to be able to map groundwater potential zones. And that was really the first breakthrough. At the same time that was happening in early 2000, 2002, we started measuring soil moisture from space. So at the same time of thermal, now we're using radar images, and we're using something called the backscatter coefficient. So as we send a radar pulse via satellite, depending on the material itself, there's going to be a different backscatter. We call that the radar backscatter. And that's going to give us an idea of soil moisture as well. And so it started with AMSR. We moved to things called SMAP, and that allows us to see the skin soil moisture. So maybe, we're talking 1 to 5 centimeters. The upper soil, they're almost the root soil moisture. And in some areas, if it's an arid environment, a desert environment, perhaps we can see as far as 1 meter, if we're fortunate. But like we talked about yesterday, since longer wavelengths have less energy, I then have to integrate it over a larger footprint. So when we're thinking about soil moisture, we're looking at 9 kilometer, 5 to 10 kilometer scale for an individual pixel. So though we can get it daily, we are pretty limited. But that, again, doesn't tell us how much groundwater is there. It just gives us some potential idea of groundwater. So really the only satellite that is capable, even today, of really thinking about groundwater storage or processes, so you're actually trying to quantify something, would be GRACE. Okay, GRACE started in 2002. It wasn't until 4 or 5 years later that they even introduced hydrologists or hydrogeologists to it. The physicists kept it for themselves at first. And then finally, it became released a little bit more to the public in about 2008. GRACE has since fallen out of the sky, back in 2017, I believe it was. And they had a brief period where they had to wait until the follow-on mission was launched. So there is about a, I don't know exactly what it is, 10-month delay where we don't have any data, but then we do now have GRACE data again. So we can look at groundwater processes from about 2002 to 2021 now. I mentioned on here where you can get the data availability. This, in case you haven't seen this before, you're going to get it from gracejpl.nasa.gov. You don't have to have the second part. That's just selecting the data. You'll notice a couple of different products. If somebody's interested in this, you're really looking at what we call the monthly mass grids, and I'll explain a little bit more of that as we go on. One of the things they also have on the website is a GRACE tool, where it allows you to look at their data that they processed. And I'm going to go through the processing techniques, but they're going to show you what they've done globally. And I want to show this for 2 reasons. One, if you were trying to get a general idea of what's happening in the United States every month, you don't have to do anything other than go to this website and select the image. Okay, that's on that same website I just gave you. And so in this particular case, you would notice that, yes, I can see that there's a depletion here, or I'm sorry, a surplus here, a depletion up here in the Northwest. But the other thing I hope you see, so this is it's very user-friendly. The other thing I hope you see is how coarse the data is. Each pixel is, again, really, it's at least, a few hundred kilometers by a few hundred kilometers. The larger the pixel, the more accurate GRACE is. For example, if I had 1 pixel the size of North Africa, it would be very accurate. If I use the number you see here, which I'm going to make up is about 30, it's fairly accurate. If I don't downscale it correctly, and I will talk about that, if I don't downscale it correctly and I just apply a filter incorrectly, I might have a very small scale. I might have 1,000 pixels here, but I promise you that they're going to be not accurate. So the smaller we filter the data, the more inaccurate it becomes. So that's something to think about. But by default, you're looking at Indonesia, you don't have many pixels. Okay. And so you have to think of a way to downscale, unfortunately, in your case, the GRACE data. And this is what I would recommend, and for 2 reasons you'll see here in a minute. So just again, some primer here. The GRACE is called the Gravity Recovery and Climate Experiment. It was launched in 2002. And the idea was we wanted to provide estimates of the terrestrial water storage. But what you'll notice is I put D terrestrial water storage over DT. It is not telling you how much water is there today. It's a big misconception about GRACE. It tells you how different it is than the previous month. It's a change in storage. Okay, we call that the anomaly of water storage. Now, there could be other ways you might estimate it, the amount total, and then change that storage. And really what its primary purpose was 2. 1, to look at long-term constant mass. We wanted to think about geologists and geodesists. We wanted to look at the mean gravity field. And then us hydrogeologists, we said we want short-term mass variation. So we want time variable gravity field, not the mean, but the time. And as I mentioned yesterday, that equates to, if we're looking at a monthly change in mass, that we're not looking at glacial isostatic rebound, we're not looking at tectonic or larger scale geologic processes. We are primarily looking at hydrologic water storage related mass variation. And that's the big assumption that we're making. Some limitations of GRACE, and I'm going to show you this throughout in some of the data, is that GRACE provides an aggregate change in total water storage. We do not get groundwater, we get total water storage, right? So that means change in snow, surface water, soil moisture, groundwater. And so a large part of the science is how do we disaggregate that total signal? Okay. I'll step back for a minute. Really what the goal of using GRACE is you download GRACE, you have to process and remove all of these errors. They don't do that part for you. They show you how to do it, but you have to apply it. Then you will actually just get total water storage. So then you have to disaggregate to get groundwater. And then of course, after that, if you want it in Indonesia, as an example, you would have to then further downscale it. So it's quite a bit of a challenge to do it, but it is possible. The second limitation is that GRACE-derived total water storage anomaly has variable bias, meaning it depends in space and time. A big problem with GRACE, because of how the data is processed in these variations, and I'm afraid to look at everyone's face when I say this for all of you living in Indonesia, it has problems with areas that are near the ocean. Okay. So if I'm looking at the central part of Africa, there are fewer issues. If I am on the northern coast of Africa, we have something called leakage error between the oceans and the lands. And so a place like Indonesia is going to have a lot of leakage error. So there's going to be some variable bias. It can be removed, but that's some of the bias. And then the last thing, as I mentioned, we have coarse, temporal, and spatial resolution. It's once a month, and the pixel size is roughly 200,000 square kilometers at a monthly interval, right? So we're looking at something like, whatever, 20,000 by 100 or something like that, or you can think of it as 10,000 by 10,000 roughly square kilometers, or 1,000 by 1,000 or something. I'm not going to go through these, but this is just an example of the GRACE processing that one would have to do when you go to that website, and they explain how to do such a thing. They do part of it. You have to do the second part. The idea is first you have to remove some sort of temporal mean. So if you wanted to look at data from 2002 to 2021, then to do an anomaly, you have to calculate the mean for that period. And then each month you're just removing from the mean. Okay, we call that temporal mean removal. You have to de-stripe the images, and I'll show you a good example of that in a minute, which means when you look at GRACE, the way the filters work is even though there are variations in mass, there are going to be these linear striping on an image. Okay, so you have to remove it. You have to apply a filter, that functioning filter that I mentioned. In this case, they recommend 250 kilometers. This is where I mentioned if I can go backwards, I'm going to come back. This is at 250 kilometers. If I go down to 50, apply 50, it's not going to be accurate. If I apply 500, it's going to be more accurate. So you have to apply a smoothing function. You have to create a water thickness grid. And then, of course, you have to look at standard deviations and amplitudes of it. So I'm going to run through this in a minute here. This was from a paper that I published 2 years ago in Morocco, where we were looking at GRACE variations of water storage variations in an agricultural area in northern Morocco, as you can see here. And what I'm trying to show is that we had both two sources of error after we even processed all of this. So the first is called leakage error. That's where I mentioned to you that depending on the proximity to the shore, depending on some other factors, you're going to get what we call leakage. And again, you can remove this, but it's just another step. And so this is to show you in our area how much leakage error there was and where it happened to be. Okay, so we had to remove this. The second is just the measurement itself. So based on how it solves these problems, some of you are, well, as you're all engineers, you probably know this even better than I, but they actually translate the gravity field mass variations to water based on the Navier-Stokes equations. And so part of that is going to induce a measurement error. And as they do that, then what's going to happen is that has to be removed. So when you're really looking, in an image, you're going to have a combination of both frequency and leakage errors. And that's something that also needs to be removed at the very end. Okay. I want to step back for a minute and give you a time where a former student of mine and I and a few others really were one of the first people to recognize that we can see a lot more from GRACE than we originally thought. So, you know, I mentioned for example, we had these striping parts. So it was known that we had to de-stripe the data because we'd see these linear trends that aren't real, we believed. But we ended up in 2011, we published a paper that says, you know, it turns out that a lot of this data is real and we need to look at. So we made some observations. For example, the first one was that we had these large persistent anomalies over long periods of time, large persistent anomalies over large periods of time. So this was in Africa, Northern Africa, okay? And what we found was we always seem to have anomalies in these areas. These red areas always seem to exist, even though this was an area that has the stripes and we thought it shouldn't. You can see some of this striping. Hopefully you can see it. So you see this light blue, light blue, light blue, light blue. Everybody see this north-south trending spots here. So that was believed to all be noise, but we said it actually is persisting through time. The second is that those same areas originate at source mountainous areas that receive high precipitation. So it turns out that when you overlay that on top of mountainous regions, the anomalous areas correspond to areas that would presumably get more precipitation or even have snow melt and so forth. Okay. The third, it was that standard deviation extended down slope and even along main channels. So what we're just looking at is that it not only included here, but you would actually see some of that going down these large drainage basins. So, you know, you might see what looked like this light blue stripe, but the reality was that was just part of a larger drainage basin. And then lastly, there were seasonal patterns in the time series of the data. So what do we mean? You would actually see a wet and dry season in the groundwater anomalies. So this allowed us to know that GRACE can be used on a larger scale. And we still have to remove some of these artifacts, but some of them are real. So what is the best way today to ensure that after you've removed all this, you have to be able to field test your data, right? You don't want remote sensing to be used and still don't have an idea of how accurate that information is and give out your create management decisions based on it. So the best way, the way that everybody would suggest is we call it an ensemble approach. And what that means is you would compare your GRACE data. So this was, again, from a published paper of mine. These are 3 different areas, but if you just look at the top, you don't have to do the other ones. This was for the entire country of Morocco. In orange is the GRACE total water storage. In purple is the GRACE groundwater storage. Okay, so you can see the groundwater storage variations through time. And what we wanted to do is we have to be able to do an ensemble approach. We have to compare it to something. So although it's not pictured here, we compared it to groundwater data where we had it. We compared it to another land surface model that you know isn't as accurate, has other pieces of information. And once we see that it starts to look congruent with one another, then we can start to move forward. So I'd like to, after giving a little bit of a primer on GRACE, I'd like to move to giving a few examples of my own research that would spur some ideas, maybe some thoughts and questions. And that's looking at aquifer depletion in Northern Africa. And I'm going to show you a number of aquifers, but in particular, Nubian aquifer and something called the Northwest Saharan aquifer. This isn't a large freshwater. In fact, it's the largest freshwater aquifer in the entire world, is the Nubian aquifer. That spans Egypt, Libya, Chad, and Sudan. And I don't know if this is a book that's often read in Indonesia, but Le Petit Prince, which is a French novella by Antoine de Saint-Exupéry that says The Little Prince. And in it, if you've ever read this little novella, it says what makes the desert beautiful is that somewhere it hides a well. And that has been so true for us for a very long time, until GRACE. We can no longer hide wells. We can actually see if there are areas of land that are being depleted. Okay, so even though this novella existed before, now we're moving a little bit different. So how do we do that? Well, again, we use GRACE, right? So just to recap, we get an aggregate water stored on or below the surface. It does this by having two satellites that travel in orbit from one another. And as one of them gets pulled over a body of mass, it changes ever so slightly its distance between the two satellites. They use these GPS satellites to know where they are. And that change in distance is converted to a mass. And then ultimately through a number of different formulations, we can get total water storage. But what that means is we're actually looking at total water storage is going to be some portion of the unsaturated zone, the saturated zone, and any storage change on the surface. So if we have very large reservoirs, that's going to impact it. And of course, all of the so we have to find a way to disaggregate that signal. That's what I mean by disaggregate. We want just this groundwater portion. So the question we had, and the question some of you might have, is groundwater being depleted in the Nubian sandstone aquifer? This is that same image that I showed you. So as I mentioned, beneath the deserts, it's the largest freshwater system in the world. It's composed of sandstones with what we call intercalated shales. It's a very old aquifer. The water in the aquifer is over 1 million years old. And so this is considered a fossil aquifer. It's not being recharged. Very little is being recharged today. And most of it was previous wet climatic period. So this is very important when we think about groundwater systems and groundwater dynamics, because this is effectively telling us that we have to be careful, that we cannot pump unsustainably. We're thinking this 3-in-1 program in part is groundwater sustainability development. Well, in order to be groundwater sustainable, we need to know how much is there and what we can safely extract. And so one of the ways to do that is GRACE. And so we processed GRACE. This is that image here on the left in the Nubian sandstone aquifer system. And what you would notice is, again, the areas in red would be where we're gaining the most water. Blue is where we're either gaining or losing in this particular case. And what we found was, from in this case, I think it was 2002 to 2011, that the Nubian aquifer system was losing 2.65 times 10 to the trillion cubic meters of water per year. Okay. And even further, when we looked at it from a countrywide specific case, turns out Egypt was the country pumping the most water. Now, that's not that surprising given their population. But the point is that this was the no longer can hide a well concept, right? We now know that they are pumping unsustainably and a little bit more than some other areas. In fact, Sudan was actually technically gaining water, in this case in the lower left. We decided to take this a step further. We did this for now all of the aquifers in Northern Africa, so the large nine or so largest aquifers. But we wanted to come up with not just looking at their quantification from the time series, but we wanted to actually not just look at changes in storage. Remember, GRACE is going to tell us changes in mass, changes in total water storage from a month to a month. It does not tell us how much is there. It does not tell us how much is there. So a former PhD student of mine, Khalil Isaac, and I came up with a methodology that we published a couple of years ago now called Groundwater Assessment. And the idea is, and I'm going to kind of walk you through it here, but what we're trying to do is take our GRACE data. So this is our GRACE total water storage. We apply land surface parameters such as soil moisture, surface runoff to get just groundwater from GRACE. This was that disaggregation signal. See? So I took my GRACE, I subtracted these land surface parameters, and now I have a GRACE-based groundwater storage change. But I want to know how much water is actually there. And then if I can combine the two, I can not only know how much is there, but how much is moving. So how do I do that? Well, first, I take from remote sensing or from field data, information on the water table and or the sediment thickness, because then I can have an idea of what we call aquifer saturated thickness. I can take the lithology plus effective porosity to get effective porosity values. I can then map my effective porosity with the saturated thickness, and I will then know, if I know how much pore space is there, how saturated the water is there, I in turn will now know how much groundwater I have. So this is think about this as a groundwater mapping technique, some of it field-based, some of it remote sensing-based, not using GRACE, but I have an idea of groundwater reserves. I combine that with GRACE groundwater changes, And really, for the first time, we can assess risk. Our paper that we published 1.5 years ago was called the Groundwater Risk Index. And the idea is now that we're armed with this information on a much larger scale, it's the first time we can really assess what's the risk to groundwater in this area. What's the risk if government changes? What's the risk, to climate change on groundwater systems? And that really, to me, as a hydrogeologist, the first question somebody needs to ask when you're thinking about groundwater sustainability. Okay. So I'm going to walk you through the first. Yep. I'm going to walk you through the first part of groundwater reserves. Okay. So what that looks like visually is we took sediment thickness maps, okay, that you can see for North Africa here. So the thicker sediments were in blue and so forth. We took the saturated thickness, taking the saturated thickness minus the water table depth, the depth of water, as you can see here, and then we get that part. We then took the lithology, so whether it be metamorphic rocks, carbonates, mixed sedimentary for the region. We assigned an effective porosity value based on that rock type or lithology, and then now we have effective porosity values. We can take those two, we can take our saturated hydraulic thickness times our porosity, and we finally get groundwater reserves. So and again, this technique can be applied anywhere to get a first order estimate of groundwater reserve. Some of these data sets might be readily available. Some of them you would have to use from a remote sensing approach or some other field data sets. I gave the papers, the names of the papers where they had global databases for this. So for example, Lask et al. Paper has a global database for sediment thickness and so on. So that's something, please zoom in the slides a little bit. Not sure how to zoom in the slides. At least I'll temporarily zoom in and then maybe come back out. But this is just kind of showing the Lask et al., Hartman and Morsdorf. And again, I will share those slides with everybody too. So don't I'll share them with Jedfen and he can share them some way or the other with everyone.
Thank you.
And so that allows us to get that part. So now the second part we need to do is calculate change, right? So I've been saying this term. So we want to do GRACE disaggregation. And to do that, we're looking at our total water storage change from GRACE. And we're going to subtract these land surface parameters. So soil moisture, surface water, and then canopy water. Okay. So I already mentioned, how do we get total water storage? Well, we process and analyze GRACE data. Okay. And that comes, by the way, from 3 different centers. So 3 different places in the world process the GRACE data, and all of them are a little bit different. But ideally, you would just download all 3 and use a combination. Okay, that's what this paper suggests. And then the second thing we want to do is actually look at land surface parameters using a global community model. Most often we use a model called GLDAS, it's Global Land Data Simulation System. And what they did was estimate all of these variables using radiative force and atmospheric forcing models. Okay. And so we can get these parameters, subtract them from total water storage, and we get then groundwater. Okay. And so after we've done that, we looked at these 9 aquifers. And what we were able to see, of course, was depending on the size of the aquifer, we were actually able to see the groundwater storage change across this region. And it turns out over the last, well, this was from 2002 to 2012, that they had lost over 2 trillion gallons of water in that area. Okay, so this is now telling the region, telling the people that this is not a sustainable system. Some had actually gained. The Lake Chad one had a gain, but others have been subtracting. So this is overall an unsustainable system. And so visually looking at some of those other results that I want to show you, I don't know if this part is showing on here. What we will notice is that this is the global map of groundwater storage. So again, remember we used the first part to estimate groundwater storage. That's what we're looking at here. We can see groundwater storage. We have larger storage in the central parts here, a little bit less here. And then this is our total water storage from the GRACE disaggregation product. Okay, so we can not only quantify how much is there, but we can also look at how much has changed in those specific regions. Once we do this, we can then estimate the loss in groundwater capacity of an aquifer. So for the entire region, we found, for example, areas in red from 2003 to 2014 have decreased by 4%. In the 11-year period, that aquifer has decreased by 4%. And remember, in this case, these are unsustainable systems. They're not being recharged today. So, we estimate that on this same exact rate, which would probably not actually be that, it would probably increase, realistically, we have 100 years or less before those aquifers are depleted. 100 years or less, 100 to 200, I should say. We took this a step further to look at variability. Right here, I'm just talking about how can we quantify it. But we can really look at groundwater variability. And this is without downscaling yet, mind you. Okay, this is just looking at variability. So within GIS, you can actually look at something called a hotspot analysis, which is looking for variations to the norm within a particular polygon, so to speak. Okay, so I can look at this area and say, are there variations to the norm through time? And the reason why that's important is because then I can address these variations and compare them to precipitation. So this is what we did. We looked at precipitation patterns and groundwater patterns. And when there are deviations of either a deep red or a deep blue, right? So we're not talking this middle part here. We're talking the dark blue, the red. Those actually show us when those are not natural climatic variations. Let me repeat that. A hotspot analysis with residual standard deviations allows us to see the difference between climate and anthropogenic because we compared it to rainfall. If they were congruently the same most of the time, then we would say, well, there is a change, but it's consistent with the climate. When it deviates heavily, like these dark areas, so not the whole area, but these dark blues and reds, that's actually a sign that there's pumping. There's a sign that there's storage changes and so on and so forth. So it's a really neat technique to be able to look at what impact we might be having as humans. And so we actually did this for what's considered the 29 largest aquifers on a study that somebody, the map that somebody else produced. We chose those same 29 and we looked at climate and anthropogenic impacts and we looked at which ones were being more climatically influenced versus anthropogenic. So for example, the Amazonian basin 0.99, that actually in this particular case suggests that we're mostly climatic changes. But you can go further south and see that some of them, particularly in Africa, are being a little bit more anthropogenic in cases. It's just an example of a project. So I'll kind of want to leave you with the GRACE part by mentioning really how do we improve GRACE, right? If we talked about we have errors and it's a larger or lower spatial resolution, how do we improve it? We want to reduce error. That's number one. We have to account for the leakage and measurement errors. And we have to account for other errors in the data sets to disaggregate that. So how do we do that? I will show you an example of this, but for now, you just take my word for it. We need to do what we call an ensemble approach. We need to compare. This is what this graph is trying to show you, that you can see all these different colors represent GRACE and hydrologic models, groundwater data, land surface models. We're really trying to compare our results and put it into context with other models. In fact, I can promise you, you will not get approved or you will not publish a paper if you attempt to just show a graph of showing GRACE. It will be rejected. It is a common practice that you have to have a comparison to some other real world variable, like a model, the data, a land surface model, and that's kind of what we're showing here. That's one of the ways that we can reduce the error or the potential for the error. And of course, the second, since we know that in this particular case, GRACE is a larger footprint, we need to downscale. If you want to use data in Indonesia, you probably have to downscale. And so I can stop here for a minute if there's a quick question or somebody has a question that they really want to get out before I continue on. But the next sort of 20 or so minutes, I want to leave enough time for questions today. But the next 20 or 25 minutes, I want to focus on some of the machine learning and science and how we downscale GRACE. So I'll see if there's any questions. If not, then I will continue on.
Oh, there's already question from Budian. Budian, please.
Okay, thank you very much for the opportunity that gave it to me. Good night, Mr. Professor Adam. It's glad to know more about groundwater analysis by remote sensing data that you explained since yesterday and this morning. Actually, I want to know more about remote sensing data. There are two questions actually I want to ask to you. The first is based on all the major hydrology variables such as precipitation, evapotranspiration, and soil moisture can be measured or estimated using remote sensing data. Improved accuracy and consistency are crucial for maximizing their use in hydrological studies. Yet its application by using GRACE that you explained before to hydrological problem is still limited by its coarse spatial resolution. How to improve those problems? Because we know that in our country, especially in a part of Indonesia, remote sensing map covered by clouds. And the second question, based on a case study in North Africa that you explained before, the hydrology data from 2002 and 2012. And I want to know, can we prediction how much groundwater available for the next 10 years by GRACE analysis? Can we know the trends from the trend data? Thank you very much.
Yeah, thank you. The two very good questions. Again, I'll start with the second. It's easier for me to remember it that way. Yeah, well, we can see a 10-year trend. We can't necessarily infer that that's what the next 10 years will be. We can try to do a statistical analysis, right? Like a student t-test or some sort of index of the, really what you would need to do is a time series analysis. You know, we would have only 15 to 20 years of a time series data, but you might find trends within the overall trend. At the very least, you know, you probably have to assume what we've seen over the last 15 years might be the continuation. That's the limiting part. Or you can combine it with other historical data not from remote sensing, right? Maybe you have groundwater wells, you know, that go date further back, and that would be a way I might suggest. The other question is, how can you improve the accuracy of these remote sensing products? That is the million-dollar question. You know, one of the ways that kind of, if I can go back for a minute, you know, one of the ways is finding ways to reduce that error. This can be in processing techniques. If you recall from a GRACE perspective, I can ensure that I don't choose a small filter. I can make sure that I do remove the errors when they do exist. And then ultimately, the more you do this ensemble approach where you not only compare the results, but also use them as the inputs, that's going to be a key part. Now, this can be done by machine learning, by the way. I'm going to talk about machine learning for downscaling, but really you can use machine learning as a way to input a number of different variables to ensure the accuracy. In my own personal research, I do a lot with precipitation. I told you I was on the NASA science team. And what we do is actually use it as comparative analysis. So we come up with quantifying error estimates. We call that looking at probability of detection, something called the false alarm ratio. We do this as a way to quantify how much error is there. And the simplest approach is just to remove the pixels or the areas that have too much error, rather than try to fix them, it's easiest to remove, but you can fix them through a couple of techniques too. So I probably kind of answered your question, not entirely, but we can perhaps talk about it again.
Okay, thank you, Professor. So to improve that, the accuracy, there are two steps by reducing error and downscaling. Is that right?
Yeah, well, to improve grace, to improve the accuracy, I wouldn't say downscaling. That's just to look at improving grace as a more useful tool. I would say machine learning, some sort of algorithm development.
Okay.
Yeah.
Okay, thank you. Thank you.
You're welcome.
Is that
Okay.
any following question? Please, if you have any question, you can directly ask the professor directly by raise your hand. And if you have some problem with your internet connection, maybe you can put it in the chat box. I will read it and maybe deliver your question to professor. Any question? Oh, Mas Panji. Mas Panji, you can directly.
Thank you. First, thank you, Prof. Adam, for presenting such a great presentation to us. In your presentation, it is mentioned that GRACE can estimate the water storage on and or the below surface. My question is, how can we differentiate the water storage between on and the below the surface using the GRACE data? And the second is, how deep is the ability of GRACE to map the water storage under the surface? Thank you.
Yeah, great question. So the first part that is through that disaggregation, right? So how do we separate the surface water like a lake versus the groundwater? Remember, GRACE just measures both of them. So the only way to do that is to disaggregate that signal. We would have to get information on the lake or soil moisture or snow cover. And you would do that through any other data set, not a GRACE-based data set, right? So you would have to get it from field data or another remote sensing product. For example, as I mentioned earlier, we can get lake levels and lake volumes from a satellite called Topex or Poseidon, and or Landsat, we can get volumes. And so we could use those as a way, if we wanted to use remote sensing, if we didn't have field data, then we would know how much storage change is happening in a lake. So we can then separate that from our signal. That's the first part. The second part is another good question. GRACE can go to the deepest part of Earth, right? So we know there's no depth limitation at that point. So whether the aquifer is, 0.1 kilometers deep or 1,000 kilometers, it doesn't matter. But it raises a very good point, because even after I disaggregate all of this, we're just going to get total groundwater change. But particularly for some of you who've had more geology, you would probably recognize most aquifers are not a standalone singular aquifer in the subsurface, right? They're generally multi-layered. You have aquifer, aquitard, you have deep ones, you have shallow aquifers. We cannot differentiate between the three, any of those. That GRACE is incapable of doing that. All we're seeing is total groundwater storage change. And so it's a big point, because a lot of times you'll see in manuscripts, or what I might see as in a review of a manuscript, is people will compare shallow wells to changes in a deep groundwater system from GRACE. And the reality is they might not be looking at the same area. Okay, so it's a key component that we would love to be able to see multi-layer systems, but really we're just seeing total groundwater. So that's a good point. But we can't see it at any depth.
Okay, thank you.
Is that any question?
All right, well then, Judge Van, if it's okay with you, then I'll continue on again for the next 20 or so minutes with machine learning.
Yes, sure.
Perfect.
You can continue.
So a few quotes that I have about machine learning. I don't know how many of you are familiar with machine learning techniques, what it really means. And so I'll give a little bit of a primer on that. Some of you, I'm sure, are really good and can probably run circles around me with machine learning. So I'll give a little bit of background, but then give some examples relating to GRACE. So, machine learning, a breakthrough in machine learning would be worth 10 Microsofts. Machine learning is the next internet. Machine learning is the hot new thing, president at Stanford. Web rankings today are mostly a matter of machine learning. Machine learning is going to result in a real revolution, and machine learning is today's discontinuity. And so the concept is that really this is, and I think it was Dr. Ramat yesterday mentioned what we're thinking about in terms of what skills for the 21st century scientists and students like some of yourselves. Machine learning is going to be a critical part, being able to understand data science. Okay. So why do we have to learn in terms of a machine learning technique, right? I'll zoom in a little bit in case it's a little bit harder to read. Machine learning is programming computers to optimize a performance criterion using example data or past experience. Can we use past variability in groundwater or example groundwater to optimize our predictions of what the groundwater might be in the future? We could do this on our own. We can't. Humans are capable of doing it, okay, to some extent, but we can only go so far, okay? We don't need, for example, we don't need to learn to calculate a timesheet. We know how to do it. We just kind of go straight forward to. But we have to be able to learn how to optimize beyond. So learning is used when we don't have an expertise. An example of this is how do we navigate on Mars? We have to think of a way to programmatically do that. Humans are unable to explain their expertise. This is a concept of speech recognition. That solutions change in time. Boy, that's called science 101 at this point. They always change. So this is an example of routing on a computer network, or they need to be adapted to a particular case. This is thinking about biometrics. Okay, so machine learning is bigger than the field of geoscience and engineering, but the concept is why we learn. What do we mean when we talk about machine learning? We're really just learning a general model from data of a particular example. I kind of mentioned that. We believe data is cheap and abundant. I know I mentioned field data wise, that's not entirely true, but I mentioned we have 50 years worth of satellite data. We have hundreds of thousands of petabytes, which is 1,000 terabytes at this point. Of storage places, thinking about Google and other places. We have these data warehouses, data marts. You think of cryptocurrencies. But the part that's expensive and rare is knowledge. Okay, so we can think about learning that way. I put an example in retail, customer transactions to consume behavior. So people who bought the Da Vinci Code, one of my favorite books, also bought The 5 People You Meet in Heaven. So that's what they happen to find as a way to learn about the people that did this, right? And so we want to build a model that is a good and useful approximation of our data. That's really why we learn and what it's all about. So now what is machine learning? Well, it's the study of an algorithm, not data, an algorithm that improves their performance at some task with an experience of the data. So we're studying algorithms, and I'll give you a depiction of this, to improve the performance of some task with experience. We optimize a performance criterion, okay, how accurate some information is. How can we reduce error? I mentioned, I forget the question, but said, how can I reduce error? First is we can ensemble approach to remove the noise, but then also we can try to machine learn to remove that error, reduce it, okay, using example data or past experience. If you think about statistics, we're really making an inference from a sample. If you think about computer science, we are developing an efficient algorithm to solve the problem and represent and evaluate model for inference. Okay, so what the heck does that mean? It means we're automating automation. If you think about, if I have a task that I want to do 100 times, maybe I want to do the processing steps for GRACE. Let's say you had 100 images. you would you could do it manually and it'd take you forever. So your advisor or you yourself says, you know, I'm going to automate this. I'm going to write a computer program that opens up the image and applies these 7 techniques. Great. That's an automated process. That's a programmatic process. Machine learning is now going to automate that automation. Okay, so they're going to develop an algorithm that would know that that's the process they should do. Okay, I know this can get a little bit confusing. So we are, another way of thinking this, I write, it's getting computers to program themselves. We don't know what the program looks like. We know how to program how to process 100 images. We don't know how to program. We don't know what this looks like. If we look at 100 years of data and see so much variation, not only are we incapable of it, we want the computer to actually be able to not just output a data set, but create an algorithm so that we can then apply this algorithm to other processes. So we write software in a bottleneck. We basically let the data do the work instead. So not us, but the data. They just look at the data. So an application of statistical learning, which is what we're really doing, is one in which identifies patterns in data and then makes predictions from those patterns. That's the key part. Okay. So I tried to make a slide here earlier today to help with this. In traditional programming, in traditional programming, we effectively take data, we write a program, we input it into a computer, and we get an output. Okay, maybe it's so maybe we take groundwater change, we add a program that automates the processing to look at storage or to remove the things and look at variability. We use that in a computer system, and lo and behold, what do we have? We have 10 years of GRACE data that looks at variability. The machine learning algorithm says we're going to take data, we're actually going to combine it with the output of the data. And you're like, well, we don't have the output of the data. We're not taking this output and now putting it here. We are actually taking data and putting it to a computer. They create a program, which in turn creates an output that they regenerate back in. This is the automating automation. And then that output goes back in on a second run into the computer and retrains it all the way back. So this is what we're really saying when we say machine learning. I know for some of you, if you aren't as familiar, it can seem like a mystifying term. So I hope I explained it well enough. The last one I have is a gardening analogy. The seeds are the algorithms. Okay. The nutrients are the data. So we have to start with the seed. We have to provide nutrients for it by providing data for it. You are the gardener. You still have to try to cultivate it. And then ultimately the plants that grow as a result of all of this work are the programs that it writes. Okay. So there are tens of thousands of machine learning algorithms, hundreds of them new every year. So before I can get ahead, if somebody asks me what's the best algorithm, there is no best algorithm, right? There are hundreds of thousands of them. I will give you the main types and then some examples of each. So the main types are ones we call supervised learning. So a classification or some regression. What that means is we are going to input training data sets. So not just the data, for example, groundwater storage change. We're also going to provide a training set for it. For example, groundwater data itself. Okay, so this is supervised learning. We're telling it this is what the output should look like. This is what we have as a validation for it. And here's our other data predicted. Unsupervised just means we don't have that. And then something called reinforcement learning, that where it goes back as iterations to learn. Okay. And every machine learning algorithm has 3 components. You can think of it as REO. It's representation, evaluation, and optimization. Okay. Representation, evaluation, optimization. What does that look like? Representation is what is the actual machine learning algorithm? Is it a set of decision tree? What are a set of rules? Do we have instances? Is it a graphical model like Markov nets? Is it a neural network? That's the one I'm going to explain today, by the way. Is it a model ensemble? How are we representing our algorithm? How are we representing our seeds in our garden? The second is how are we going to evaluate it? There's no point in having a model if we said machine learning is to create a and improve a performance evaluation criterion, we have to have a way to evaluate it. What's our accuracy? How are we going to look at precision and recall? Are we going to look at squared error? Are we going to look at entropy, KL divergence, a number of different ways that we can evaluate our actual plants in our system, okay, the outputs. And then lastly, optimization. I won't go into this, but there are a couple of different called combinatorial, convex, and constrained. This is just how do we optimize our models? We're going to get a result, but can we improve even that result after it's done? So I'm going to go through examples of one of them, supervised learning. So this is an example of how can we use a decision tree tool that creates rules. Why do we do that? Well, maybe perhaps we want to predict a future case. So we use a rule to predict the output for future inputs. Okay. Predict the output for future inputs. So, an example of that would be, we want to use some combination of data to predict that groundwater changes in the future will have an impact on, lake levels, for example. The other thing might be knowledge extraction. So the rule is easy to understand. We want to make something simple, even though we might not see it. An algorithm can do it. Compression. Maybe the data or the rule is actually simpler than the data looks or explains. So we're going to create a simplified rule. And then maybe we can look at outliers. So exceptions that are not covered by the rule. So these are uses of supervised classifications and supervised learning. I'm mentioning one paper here. This is, if you were to read no other paper, I would recommend this paper to understand machine learning for what I call the geosciences. And it's by Carpentier in 2017. It's called Machine Learning for the Geosciences, Challenges and Opportunities. Challenges and Opportunities. And really, they looked at three main parts. So challenge or opportunity number one is there are inherent challenges in geoscience processes. Why do we do machine learning? Because we have amorphous boundaries, because we don't have stationarity in our data, because they're multivariate and they're not nonlinear. Most of our processes within geoscience or engineering, they're nonlinear. We can't create a simple function to do it. We don't have boundaries that are clear cut. We don't have stationarity, that things change through time. And so because of that, we have to create. Humans are incapable of solving these questions on our own. The geoscience data collection challenges, data from multiple sources, different resolutions, different errors. I'm looking at 20 different data sets from remote sensing now. Each one has problems. Each one is coming from a different source, has a different spatial resolution, a different temporal, has inherent errors. How do I grapple with that? And then lastly, the one I've been harping on, we have a paucity of samples and ground truth data. We basically lack what I would call the gold standard. Okay, so we're lacking that data. And so what I'd like to do is give you an example of one. I'll briefly explain what artificial neural networks are, ANDs as we might call them, and show you how we've done this with GRACE. So a neural network, I'm going to zoom in a little bit. Basically, a biological neuron receives input from other sources. This is how it is in the human body. Combines them in some other way, performs a generally non-linear operation on the result, and then outputs the final result. Okay. So for example, we have a synapse here that has some electrical contact between the neurons and sends it out. I won't go too far into the biological part one because that's not my expertise, but it's not also as relevant. And so in an artificial neural network, the one we're creating, it's a network of simple elements called artificial neurons, which receive input. They receive input. What's the input? That's going to be data. They change their internal state. They become activated, okay, according to that input, and they produce an output depending on the input and that activation. And the network works by forming, the network forms by connecting the output of certain neurons to the input of the other neurons, formed a directed weighted graph. Okay. What does that mean? We take our inputs, we have a weighted component to them, we have a net input function, and it becomes activated to create an output. And then this again can in turn, we can go back and improve it from there. We choose neural networks. There are other ones. One of the reasons we like neural networks is because they have a high capacity or penchant for establishing complex and non-linear relationships. Okay, so if you have more non-linear relationships, this is one machine learning technique that fits very well. Okay. And so what I'm going to show you is an example where we take in situ observations, our models, some remote sensing, some other geospatial analysis, and we create a machine learning neural network. We use GRACE. This is where I mentioned, this is what the GRACE satellite looks like. We're looking at the equivalent water height of everything. We're trying to get just a saturated condition. As a reminder, the limitation of GRACE is that we have aggregate changes. Well, we can solve that by disaggregating. We talked about that. We have an anomaly both in space and time. While we can do the GRACE processing to remove errors. And then our last issue is we have coarse spatial resolution, 200,000 square kilometers. That does not work at all for Indonesia. So now we can use machine learning to downscale, not only improve maybe the GRACE accuracy, but to downscale GRACE to a smaller resolution. So if you think about it this way, GRACE might be this entire pixel here over the land surface. But if I know the variations in other hydrologic components or biophysical parameters on the surface, that probably informs me of what might be happening in the groundwater. And then I can test that using groundwater wells. So the objective for this particular study was, can we evaluate both GRACE-based estimates and total water storage, combining that against hydrologic models? So this is a way that we're going to reduce that error. And then secondly, combine it with in situ observations. So I'm kind of stepping back a little bit from machine learning for a minute, because this is an example that uses both. But this is where we take our GRACE-based analysis, we then combine and create an integrated hydrologic model. So this is a surface groundwater model using field data sets. So we developed a model in Mike Shee, and then we were able to then disaggregate the signal using a hydrologic model. So we analyze our water storage variables, we predict high resolution anomalies from GRACE and other data set, and then we validate it using in situ and model data. We did this for an aquifer here in the United States. Just to remind you some of the processing techniques, we have to look at a number of different data sets, remove the leakage and measurement errors that we talked about. And these were some of the data. I put it on here mostly for the slides later. I'm not going to talk about them too much, but this gives an idea of the data sets we used to get those land surface parameters. We also had to remove lag, right? So for example, we know if we're trying to look at a link between surface parameters and groundwater, we know that they're not linear. We know that they're not in the same time scale. For example, if I'm looking at vegetation, after it precipitates, vegetation doesn't have a direct response. It's gonna take X number of days. It might take 3 days, it might take 2 weeks to create a vegetative response. And then even after the vegetation responds, how long after the vegetation responds does the aquifer actually become recharged? And that's what this is showing. So if there's, this kind of shows you the amount of lag between storage change and vegetation. And what this allows us to do is then put all of these data sets on the same scale. Okay. And so we created an artificial neural network to establish a complex empirical nonlinear relationship. And so our inputs, as it's just a few examples, we use precipitation, land surface parameters, standard deviations of water, surface discharge, soil moisture, vegetative content, for example. So we put all these inputs in from satellite-based, for the most part, satellite-based measurements. We had a training of our data. Training, so you have to train your model first before you use it for prediction. So we trained it and validated it. We had a performance criterion of looking at R squared, Nash Cliff, for example. And if it did not meet our criteria, we go back and we train it again. If it did, it creates our function. This was that program that it creates. Once it creates this program, this function for us, we can then apply it back in and actually get our output. So now we're looking at GRACE, or it outputs the total water storage and the program. We can then take this further and apply that same input data again on a smaller scale. So right, this is the whole image. Now I'm zooming in, apply it to the function, and now we have GRACE at a smaller resolution. So this is what GRACE looked like before, and that's based on this exact size of the total image here. Now what I can do is subset the image, but apply the function that we've learned, the program that it's created, the plant, if you think about the gardening analogy. And now I can see very small scale resolution changes. So this is really what we're doing. This is busy, but I want to try to explain it a little bit. So the process, really what we're seeing here starts at the top, works this way and then over here. So really what we're doing is we have a study area, okay? We have some training wells, maybe it's groundwater wells. That's what these little points are. We have individual points. We don't have data for the entire site, but we have data points. We apply the training based on all kinds of data, precip, land surface temperature, aquifer thickness, whatever you think impacts groundwater in your particular region. And we iterate those different data sets through time. It then predicts in those same locations what the storage changes. That's what this half purple represents. Okay, so we match it with our observed, it predicts what we have, and then we use our predictors to once again predict and train again. So what we end up getting is a prediction of points, and ultimately then we have our finalized prediction. So really it's just going through this part, but just in a little bit more scientific way. In our particular case for this study, we use something called a feed-forward neural network and some back propagation algorithms. We had 6 input data sets that you can see here. We created 70 neurons. That means 70 weights to this hidden layer. And then ultimately we have 1 output. Okay. And this is a good rule of thumb. Of our training points, we split them up. 70% was used for training in our supervised technique. This is a supervised technique. We used 15% for validation and then 15% for testing. This is, if you would ask me this question, this is a good breakdown between, how much we should use. And so what does that look like? Well, it turns out that our simulated water storage change is in blue and our target was in red. So we compared the the groundwater gauges or wells to our gray-spaced water storage changes on a smaller scale or better resolution. And you can see it has a very high accuracy at a small resolution. If you're looking at a plot here of target versus output, you would see in the training, we have a high correlation. The validation, it goes down a little bit. Our test, it's improved a little bit after we retrain after validation. And overall, we have a 92% accuracy, so to speak, with how accurate our downscaled GRACE data is. And so what that allows us to do now is apply this to a much larger watershed area. And we can even look at what it means in particular watersheds. And that's really kind of what I'm showing here. We have groundwater levels. These were our training data sets. We had some stream flow. And now we're able to predict GRACE and groundwater on a much smaller resolution. I'm showing this graph because this isn't one single program, one single machine learning model. What you end up doing is running through hundreds to thousands of these. It does it for you automatically once you set the program up. And to give you an idea, they'll show you that in each iteration, what input parameters were used and the output RMSE. So for example, in this AN number 6, primarily it was influenced by land surface temperature. And we had a higher RMSE when we used only land surface temperature. So this tells us the sensitivity of the input. And this one was more sensitive. Conversely, ones that used an all-around approach and maybe vegetation and soil moisture, those were the best predictors of groundwater storage change. That's what this is saying. Those are the best predictors. So this is a powerful output, not only as the input, but as an output. And so kind of thinking about all 3 of them, how do we get the best GRACE-based solution? Well, we have to combine GRACE with models. We can calculate for subbasins. We want to combine GRACE and compare it to land surface models. That's what NOAA and BIC are. And then we want to calculate and combine and look at versus groundwater level. So you might not have all of these. You might say, well, this is great. I finally figured out how to process GRACE, but I don't have a way to validate it. I don't have validation or training data sets to create a machine learning algorithm. Well, in this particular case, you could either use groundwater data, you can use a global land surface model like NOAA or VIC, or you can develop your own hydrologic model. So I'm kind of just giving you 3 techniques that we did, but you can do any of these 3. And I don't really want you to focus on the results per se, but this is why it looks a little bit busy, but all of those things are on the same graph now, right? So the groundwater depth is shown here in purple on the top, the neural network is in blue, the integrated hydrologic model is in yellow, and these other land surface ones in the other color. So really, this allows us to see that we are within reason, and of course, we can do statistical evaluation of that, and that's what we've done. The second way, and this is where I'm going to go a little bit less detail on, is through something called the boosted regression tree. Okay. And really what this means is we're going to take a parameter. In this case, we're thinking about stream discharge. That's the example I'm giving here. And we're going to now say, if we run it as 500 cubic feet per second, what impact does that have on groundwater storage change? And then we're going to give it a tree, a decision tree. We're going to break it up. It's going to automatically give it at 1,000 and then maybe see what the storage changes as a result. And it's going to keep doing this decision tree over and over. And the reason we do this is we need to create a model that is a linear now, linear, not nonlinear, linear combination of a weak learner. What is a weak learner? A weak learner is you're excited, you found a machine learning algorithm like an artificial neural network, you have the data, you have grace, you have the training, you are ready to complete it all. You run your neural network, but guess what? It does not look like this. It might, but it might turn out that your training and your validation has like a 0.3 correlation. That's because your inputs are what we call a weak learner. It doesn't accurately predict the system. In a neural network, there's not much you can do. What you would need to do is find additional input data. Another, like maybe you're thinking you would need to know the glacial deposits. You would need to know surface storage, and that you would have to hope that it works. In a boosted regression tree, it adds just another tree. So it combines all of these weak learners to create a mega learner. So see, you have these deviations from these weak learners, and through number of trees, this is from 0 to 7,000, at first you have a bunch of weak learners that don't show the variance very well. But then the more and more trees that you have, the more and more decisions that it makes, you now have a more accurate result. So we call this boosted regression trees. I guess I probably won't go through some of these results, but this is just going through, real versus a predicted neural network. So this is a paper we published recently. You can see in this particular case, this was real data versus a neural network. This is real data versus a neural network modified. This was real data versus a boosted regression tree, and then through a predicted land model. And what we found, even though they all look pretty similar, statistically in this case, the predicted boosted regression tree even outperformed our neural network, but that doesn't always have to be the case. I say this because there is no perfect model. We did, again, another testing for a different site. That's what this is showing. And it allows us, as another study that I'm showing you, to look at spatial predictions. So now that we finally downscaled GRACE, we can look at groundwater pumping. That's what this is showing. Basically, groundwater storage changes due to pumping in an aquifer here in the southeastern part of the United States. And I think with that, for now, I'm going to stop, and I'll take as many questions as you want to give me. And thank you so much, Terima kasih, for all of your time, your energy, and your passion. And please feel free to reach out into the future if you have questions, and I'll be happy to take questions and share these slides. Thank you.
Thank you. Is there any question for Professor Adam? Anyone? Oh, Faisal. Please, Faisal, for your question.
Thank you, Prof. Adam. So yeah, I would like to ask us just maybe particularly because nobody asked you yet. So yeah, I'm just giving myself a chance. So I'm particularly interested. Oh, before that, I would like to show you this. Maybe you still.
You know, I was going to wait to comment. I was going to let you. I saw that. Thank you very much. I
Yeah.
appreciate it. I have in my office. I have my Georgia football helmet.
Yeah, I still have this intact since 8 years ago, and I think I'm kind of still I'm kind of starting to fill this up because my body mass is increasing.
Well, that's still good. 8 years later, that's great still.
Yeah, it's good. It's good. So anyway, so my question is, so I'm particularly interested in how the the some of the last slides of yours work about the the downscaling technique, but calibrating it to a model. So it's kind of model calibrating to a model. Is that what your last slide saying?
Yeah, well, so that model was it was calibrating to the model, but the model was the training data. That's what those last few slides were showing. So it was comparing the neural network based outputs to the training data. Our training data in this case were groundwater wells. So we had the inputs of these other parameters. Our training our data set, our proof, our validation data was groundwater wells. And so we split them up. Roughly 70% of that went into creating the neural network, to train the neural network. And then we split the rest as 15% validation and verification. And so when I showed you those plots that looked at target versus simulation, really what we were looking at was the neural network predictions or the machine learning prediction compared to our gold standard, which in this case was a groundwater well. Other times, though, I tried to show that our gold standard, we didn't have groundwater data, or maybe we did, but very little. So we created an integrated hydrologic model, or we used the global land surface model, right? So if I were to think about this, the best case scenario would be groundwater data, right? But you might not have it. The second best case scenario would be to create your own hydrologic model, an integrated model, from other sources. And then the third would be, I'm going to use a global land surface model. It's not great, but it's something. And that's really what we were looking at.
So yeah, so then my question is, so how do we deal with the chain uncertainties? Because in such a integrated model, we have uncertainties. Then that model is we use that to calibrate our machine learning. And before even in the field data measurement, there's uncertainties as well. So how do we deal with that?
We don't. Now, we attempt. Okay. So one of the things we do, and I don't have a slide for it, unfortunately. Let me see if I have an idea that I might think about. It's kind of looking at things like these. Okay. So there's no perfect thing. It is such it's probably the best question so far. Is the best question to really ask in general about science, in my opinion, about remote sensing. We call it, right, the propagation of error. The more complex you get with things, if we're just collecting field data, there's one error, the data of the error of the
measurement.
The measurement, the device itself, right? Maybe a human error too, but that's it. Then all of a sudden you put it into a model. Now we have that error plus model error. Then we put it into neural now, and it's propagating, it's adding up. So we can't remove that to any extent. What we can do is try to measure the impact. And I don't have it. This is discussed in some of my papers, and maybe that might be the easiest way to share it in the future. But what we'll look at is what is the impact of particular data sets, number one. That's one way we can do this. So we can look at this and say, which ones are the most influential? And if it turns out that it happens to be soil moisture, and then we know that soil moisture was measured in the field and not the integrated hydrologic model or some remote sensing, then we feel more confident. But right, we don't, and we can even quantify it to some extent, but that's kind of as far as we can go. So it's, and then there are a couple other ways, but all we can try to do is quantify how much is there and to provide an error bar. And so in fact, I'm gonna have to go way back now, but I will show you. Hang on, give me a second. I'm getting there, promise. this. That's why all of these green and purple error bars exist. So I'll zoom in a little just to see, if our neural network is in blue, these errors are our quantified version of total error that we would suspect. Now, again, are we maybe underestimating? Sure, right? We can't be perfect either. But it's quite large, that amount of error. And so we can do a couple of different ways to quantify. Yeah, great question.
Thank you. Thank you very much.
I think the second question is from Novia. He put her question in chat box.
Okay. Regarding the training data set, several researchers use 70-30 for that. Would you please tell me why? There is no reason why. Yeah, every time it's amazing. Humans, we always try to figure out reasons to things. There is no reason. Somebody just started with it. They published a paper and everybody followed. So, you could use a different ratio. 80-20 is perfectly fine. That's okay. 70-30 just seemed like a good fit for somebody originally, and that's just what we use. But I have seen others that do like an 80-20 or an 85-15. But 70-30 is generally what we use. I do a lot of hydrologic modeling, and in our case, we split it up between calibration, validation, and post audit, and we tend to do a 60-30-10 in that regard. Okay, but so 70-30 is fine. Or if you change it, that's okay too. The test data set is selected by, it means that they can select the representing data and they finally get the good performance of their model. Not necessarily. So they're just, they're selecting the final output, but from a downscaling perspective, right? So they're downscaling it and they want to make sure that this prediction that the neural network has come up with, it does represent something real. And so they need the test data is a way to show, it helps train that data. So yes, are we inferring that? Well, actually, I'm going to step back. It's a good question because we do actually test for this. What we do is we use that output data as our training, and we test the influence it has. I wish I had a graph of it now. I don't have it. We test the influence that has on our neural network. So there is a way in an actual number we can get from that. So that's a great question, but we can make sure that that's not happening in that regard. And again, we don't use it as input data. It's just used as the evaluation at the end. Okay, in my case, I don't use neither that. So the test data set, I assume you mean the validation data set. That would be either groundwater wells, land surface model, or hydrologic model. Your inputs would be parameters that influence groundwater. If that makes sense. Any follow-ups you can ask. But Novia, I don't see your Georgia Bulldog sweatshirt on.
Okay, maybe the next question is from Pak Putu. Pak Putu, please.
Okay, thank you. Hi, Prof. Adam.
Hello.
Thank you for the time. Yeah, it's very interesting talking about the machine learning. Yeah, we know that there are several methods in machine learning, as you mentioned in your presentation. I usually use artificial neural network too. Yeah, in making prediction models in hydrology or hydrogeology. Now, my research in prediction in groundwater table fluctuation with artificial neural network. My question is how to combine remote sensing and artificial neural network in modeling water table fluctuation as a hybrid model. Can you explain about the combination, Prof?
Yeah, I think a little bit. I'm probably just going to speak a little bit too broad, and if you want to follow up, you can now or in the future. But you know, that really is what we're trying to do at when we talk about these last two presentations is how can we integrate remote sensing to what some people might be doing already, right? So it sounds like you, Puto, have already been doing neural networks using some field-based data, and you can see water table fluctuations. You know, ultimately, a remote sensing just provides additional, in my opinion, additional training inputs, right? If you think about it, you know, maybe your prediction of your neural network used, you know, 4 or 5 other field parameters, and it can come up with a pretty good representation of what's happening. I view remote sensing as one that can either broaden its scale, right? So maybe now we use your same field data sets, but you now combine it over all of Indonesia. I'm assuming this is in Indonesia for a second. And so remote sensing can be used to broaden the scale. That's one thing. Other thing is it might be able to better predict or better create weak learners to strong learners, right? Because now all of a sudden, perhaps, you know, you have a remote sensing parameter that better predicts that output, if that makes sense. And then maybe specifically for your question, how can we use remote sensing to look at a water table fluctuation? I would think exactly the potentially the GRACE data set. That, to me, that would be showing you groundwater storage changes. It's not going to predict the height of the groundwater table, but you're going to combine your already neural network with additional groundwater from GRACE, and you'd be able to probably better predict those changes. That's what I would assume, you know, off the first go.
Okay. Maybe you can share the sample of reference, yeah, about the combination using of remote sensing and machine learning. Maybe we can study for the topic, yeah.
Yeah, you know, I'm willing to share what anybody wants. What I mean by that is all of my papers I have as PDFs. I can share all of those files. Much probably like all of you, I create reference databases for machine learning papers, for GRACE papers. I am willing to share all of those. And so, you know, those databases probably have 100 papers in them. So you can, on your Saturday afternoon, you can go through them and enjoy them anytime you'd like. I'm more than willing to share that. Yeah, and then again, answer any follow-up questions.
Okay. Yeah, I'm already read your paper, several paper. Yeah, very, very interesting.
Well, thank you.
Yeah.
Yeah, like I said, you know, if you or anybody wants them again for whatever reason, or if there's a follow-up question, feel free to let me know.
Okay, thank you, Professor.
That any question? If no, maybe I have question for you too, Professor Adam, regarding yesterday. I really curious about is that the measurement by satellite can predict or maybe can show us about land subsidence over in the land. Is that possible to predict, or maybe we can see the difference between before and after getting land subsidence?
Yeah, so I had the one slide about it yesterday, and so perhaps I can talk a little bit more about it. I'm getting there, I promise. Okay, so the land subsidence isn't by GRACE. We use a radar image. And if you recall in radar images, as I mentioned, I'm going to zoom in here. With radar images, we're looking at something called a backscatter. And so the way that works is we use something called interferometry, or an interferometric phase analysis. So when we get a phase of a radar image, what we're actually looking at, okay, is the displacement of land, impacts from the atmosphere, impacts from topography, impacts from an orbit, and then any noise we have. Well, it turns out, in theory, we can remove all of these other parameters. We know the orbits because we know that precision of where they are. We can attempt to remove the low noise. We obviously can remove what we call baseline by knowing the topography of a site. Okay, and then atmospheric impacts. It's hard, but we can mostly do it. And what we're left with in a phase shift is something called displacement from one image to another. So if we compare the phase diagrams of two images, so we're not this, when I say a phase, I don't have a picture of this. We're not seeing an image like I think somebody asked yesterday, we see Landsat, we see a visual image. When we're looking at these radar, what we're actually seeing is the radar wave. It's phase. So how many times it goes in and out of cycle. And so when we compare two phases together, we can then remove that and get displacement. So yeah, we call that radar interferometry. This technique in particular is called persistent scatter technique. And so we used about 80 images, 80 radar images, and applied this technique, removed all this noise, stacked the data into 80 images, and then looked at how much displacement was happening over time. And that's what we're seeing here. And so we get individual pixels. We don't get this whole image. We get individual spots of land deformation. That can be growing too, right? In some cases, this purple is areas that gained land. And if you look, that probably makes sense because these are probably aggradation, like delta or like alluvial fan deposits that developed. Okay, so the land actually had grown. There's more deposits, and then some of these areas are depleting. So that's what this is kind of showing.
Okay, is it also possible to implement in nearly coastal zone? Because as you mentioned before, we maybe got some problem to detailing when it near the water body itself. Is that possible during because
Yes.
maybe backscattering satellite?
It is. In fact, by the way, this is a coastal city. So right here off this map is the Atlantic Ocean. So this is in Morocco and the Atlantic Ocean right here. This is a city called Agadir. This is just looking up. So yes, radar doesn't have very many issues with water like GRACE does. So radar has no problem. That can be readily applied. It's not easy, readily applied in Indonesia.
Okay. Thank you, Professor Adam. I think, unfortunately, the time is limited. I think this is a very fruitful discussion, but unfortunately, the time is limited. So I think we must wrap this discussion, this lecturing, and it is a great opportunity for us to have you to lecture us and deliver your new information for us, especially for students. Maybe if their topic about groundwater and remote sensing, I think this is a new knowledge to them. Thank you, Professor Adam, for this opportunity and this fruitful discussion. Maybe I represent the Water Resource Department. Want to say thank you for your coming and giving the material. And I also want to say so sorry for the question that maybe cannot answer directly by Professor Adam, but I promise I will send him an email regarding the question from you, and I will inform you if you if I get feedback from Professor Adam regarding your question. Thank you, Professor Adam, for today. I think it's wonderful and very interesting topic for everyone. Thank you, everyone, all of participants. Maybe we can hope to have an opportunity again to discuss about groundwater and remote sensing analysis and the technique in the future. Thank you, everyone. Thank you for Busi as head of department. Thank you for